Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my channel and also request that we members subscribe and also ring that notification bell to be getting updates on our various uploads. And also I'd like to encourage our members to be checking our description boxes for various links of other similar videos. Now in our discussion today, I'm going to have a first and second bit of the discussion on the concept of Kirchhoff's law. And this is going to assist us in trying to identify some of the basic laws which we are going to confine ourselves with, in especially trying to deal with the flow of currents across a circuit, or of finding the potential difference across various components in a given circuit set. Now, in this particular case, we're going to rely heavily on this specific aspect of the works of Gustav, of course, Robert Kirchhoff. And this is, of course, going to be assisting us in trying to evaluate various potential differences that we're going to see being, of course, either passing through the various components which I have just given on the board. Now, this is going to be in set of three sets of circuits which I've given, which basically are going to assist us in trying to evaluate what I've just mentioned. Now, Gustav Robert Kirchhoff was a German scientist, and of course we're going to see that him together with other scientists like Robert Bunsen are going to be providing us some of the clues which we are going to see in various topics which we are going to discuss. And of course, especially on various aspects of the topics of electrical circuit spectroscopy and some aspect of thermophysics or chemistry. They're going to be providing especially some fundamental equations which are going to be assisting us in trying to, of course, understand various concepts. Now, in this case, I've just mentioned the two individuals intentionally. Now that we're going to discuss on the works of the first one in order to assist us trying to evaluate some electrical circuit, of course, diagrams. The second one, together with the first one, of course, they did some fundamental roles in trying to advance various topics, especially in sciences. And in this case, we're going to see that some of the aspects like the Kirchhoff circuit laws and the laws of thermal radiation are going to be part of the works. And of course, we can see that from Robert Bunsen, there are some various aspects of experimental data which we get from some of the equipment which were developed from these specific scientists whom we're going to name by Robert Bunsen. Now, we're also going to appreciate that some of the terms which were coined, like the black body, associated with Gustav Robert Kirchhoff. And those are some of the works which we are going to come across. Now, the two individuals together discovered some of the elements which we are going to see in our periodic table. And those are, of course, the elements of cesium and rubidium. And this, from our last discussion on the concept of the periodic table and the periodic trends, these are, of course, the alkali metals which are going to be, of course, the group 1 elements. Now, in this case, these are credited for the discovery of the two elements which you have given for cesium and rubidium. And of course, those are, among others, are some of their works which we are going to be appreciating as we come across them in our various discussions. Now, in this case, going ahead, then therefore, I'm going to use the above illustrations in order for us to understand the concept of Kirchhoff's law and the Kirchhoff's laws and some of the associated laws which we are going to come across in our various discussion. Now, this specific aspect is going to give us basically an evaluation or an understanding of Kirchhoff's two basic laws. And these are going to be the laws which are going to be based on conservation of electric charge and, of course, the potential in various aspects of this specific circuit. So in this case, I'm going to mention the laws. But as I've said, the first law is based on conservation of charge, which in this specific case is an electric charge. And of course, the second law, which is Kirchhoff's second law, is based on the potential. Now, in this case, we are going to give it in terms of illustrations. And of course, that's going to assist us in trying to understand what basically this law states. On the first one, of course, which is based on the potential, it states that at n junction point, the sum of all the currents entering equal to the amount of current that is going to leave that specific junction. And in this case, we're going to summarize these specific laws that literally saying that whatever goes in comes out, and that is going to form a Kirchhoff's first law. And of course, that's going to be giving us an essence of what basically this law entails, as we are going to discuss it in details. Now, in this case, we are going to also to look at the second law, which is based, as I have said, on the potential. And of course, it's going to state that the sum of the charges or in a potential around a closed circuit or path is equivalent to 0. And in this case, we are going to also look at of course, other forms which, of course, are going to state that around any closed loop in a circuit, the directed sum of the potential difference across the components is going to be 0. Now, in this case, we're going to also look at this specific aspect of, apart from the conservation of charge or electric charge, there's an aspect of the potential for a closed loop, and that is going to assist us understand the concept of a Kirchhoff's law. Now, for my illustration above, I've given 3 circuits given as A, B, and C. And of course, I'm going to identify them from the 2 basic laws, which I've, of course, read out for the Kirchhoff's law, so that the assistants understand this specific aspect of the Kirchhoff's law in terms of conservation of charge and the potential given as such. Now, the first circuit is going to consist of a closed loop with a power supply. And of course, I'm going to just give this one in summary form so that in comparison with others, they're going to be making some sense for us. So this is going to consist of a closed loop, and it's going to also consist of a power supply. So there's a potential or an electromotive force which source which has been given in terms of this specific junction of a V1. And then for the second circuit, it is going to be consisting of a loop, of course, without a power supply. And this, of course, is going to be, of course, a loop, a closed loop as well, but without a power supply. Let's just indicate this one as V. And then we're going to, of course, it's not going to be a V, but without, let's just give it as a power supply to avoid confusion in this particular case. And also looking at the third one, we're going to see that it's also not going to be having a power supply, but it's going to be indicating, so in this case, it's also a loop, but it's going to be without power supply. But there's a unique case which I've left for the third one, which we need to identify. And in this case, if you try to look at this one, there are various aspects of the rules which we have mentioned for, especially the direction of current, especially being given the source of electromotive force. And in this case, we mentioned that for cells, the positive, of course, a terminal is going to be assumed where the current is going to flow out. And therefore, in this case, we have given this specific direction for the current flow, which has been given as such. So in this case, we're going to assume that the cell are going to provide the direction of a flow of current given in this specific direction from the positive terminal. Of course, it's going to flow out using that one. But if we consider the second one, we're going to see that in this particular case, we're going to see that there's no source of electromotive or power supply as we have indicated on the board. And therefore, we're going to assume that the components, we're going to assume that the positive is where the current is going to flow into the components. Now, in this case, we're going to see like this one, of course, we're going to have V2. So for the positive, the current is going to flow into the components indicated using this specific direction. Now, in this case, we're going to see that from Kirchhoff's second law, we can indicate that the V for this specific kind of circuit, as we have said, which is going to be consisting of closed loops, is going to be equivalent to 0. Now, in this case, there's a specific way in which we are going to be applying this specific principle of the second law of Kirchhoff. And therefore, we are going to be assuming that for the second case, unlike the first one, whereby we have identified the source and the direction of currents, this specific current is going to be assumed to be, of course, flowing using this particular direction. But as we're going to see later, the contrast between B and C, there's going to be a case whereby this specific aspect of the Kirchhoff's second law is going to be applied, whereby we're going to see that in assuming the direction of flow of current, this is going to be violating some of the rules unless we have an additional condition which we are going to be attaching to this. Now, in this case, if we look at this one, we are going to assume that the direction of this specific current is going to be achieved from the external sources which have been given using these added wires in this particular case. And therefore, for us to contrast this second and the third one, we're going to see that there's a difference in the direction of flow of currents for the V1, which we have given in this specific case, in a sense that in this second case, the flow of currents is going to be towards this direction, whereas for the third one, we're going to see it's going to flow into this V1 from that upper direction. Now, if we assume that is the case, then therefore we're going to see that for us to obey the Kirchhoff second law, there are some of the conditions which we are going to be having in order to assist us have a clarified way. And of course, we're going to see that the current must enter and exit the loop, especially for the this specific aspect of. Now, suppose we look at the equation which we had given for illustration of Kirchhoff's law. This is going to be given in terms of V1 plus V2 plus V3 plus V4. And the sum of this current is going to, the sum of this specific potential which we had mentioned is going to be equivalent to 0. Now, in this particular case, if we try to look at this specific circuit for 2 and 3, I can give another version which is going to be still from the second law of V1 minus V2 minus V3 minus V4 is equivalent to 0. Now, for these two specific conditions for the circuit, the correct circuit to obey, of course, the Kirchhoff second law, we are going to see that for the first case, we give this one as 1, and then give this one as 2 respectively. Now, for us to obey this Kirchhoff second law, we are going to see that for the correct circuit in this specific case for B and C, which we are assuming that the current sources are going to be, or the circuit has been connected to the external source, we're going to see that one of the values for the first condition has to be negative for it to obey this, of course, Kirchhoff's law. As we're going to see, these are going to be having a sum which is going basically to be, suppose they are going to be positive, then therefore we're going to see that there's one of the way in which we can have this specific condition obeyed by having either one of the values of this or some of the values being negative. And in this case, if we consider the flow of current for this one, it's going to be going in a positive direction as compared to this one, which is going in a positive. But one of the aspects of this specific V1 is going to be a negative. Therefore, we are going to assume that for this specific condition to be true, that one of the values has to be either negative or positive, then therefore, as in the case for this second one, then therefore we're going to see that the second circuit is going to be, of course, indicating the correct flow of current. And this is going to be indicated using this specific opposite direction. Now, we can show that one using perhaps an evaluation or just a simple example by allocating these various potentials, the values. Now, suppose you have V2 equivalent to V3 or equivalent to V4. Now we're going to look at the contrast between this one and this one. We're going to see that if this one perhaps is equivalent to 2 volts, and this one 2 volts, and this one 2 volts. And the total for these ones, of course, from this specific evaluation for 2, 3, and 4 are going to be 6 volts in that particular case. So for us to have this equation, we're going to have V1 plus 2 plus 2 plus 2, and then equivalent to 0. So V1 is equivalent to, or V1 plus 6 volts is equivalent to 0. So V1 is equivalent to negative 6 volts. So in this case, as we said, one of the values has to be a negative in order for us to be obeying this specific condition for Kirchhoff's second law. Now, in our next discussion, we're going to look at another evaluation which is going to shed more light for us. And of course, from this specific evaluation, then therefore there are some specific conditions which we are going to be abiding by in order for us to obey the various laws which we are going to be coming across in our various discussions. So kindly check our description boxes for various links as indicated earlier. It's going to consist of a link of similar discussions which we are going to come across in our various discussions and similar topics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.